Hi class, welcome to week 1 review video part 2. In part 1, we talked about, I'm going to scroll up on my outline here that I made for this occasion. Part 1, we talked about minerals, so there's a lot of good information there that's on your test that you will take this week. Please watch part 1 before watching part 2. Part 1, we also talked about how rocks are classified and identified. We talked about 3 types of rock. And now we are ready to talk about the rock cycle. So we want to know that the rock cycle is continuously occurring. It's been occurring for millions, if not billions of years. And this happens due to the plates moving. The lithosphere, which is comprised of the plates, is in constant motion at our 3 plate boundaries here. So because of the plate motion, we have the rock cycle. So that means, whoops, why is my picture not showing? There we go. So that means each type of rock can turn into the other type and actually turn back into its original type. So we talked about when we ended volcanoes that all rocks started off as igneous rock because when the earth was forming, it was not a solid, but it was kind of like had a liquid consistency because it was so hot it had not yet cooled and solidified. So all rocks started as igneous rock, and if igneous rock meets a subduction zone, so this occurs at a convergent plate boundary, it can actually melt back into magma, cool again to form another type of igneous rock. So igneous rock can melt and cool to form igneous rock. So if we have an example of igneous rock, like obsidian, okay, that is an example of extrusive. That means it occurred on the surface from lava. So we have igneous rock, like obsidian, that cooled on the surface, known as extrusive igneous rock, meets a subduction zone. It can melt again and maybe transform into perhaps granite, another type of igneous rock. If igneous rock or metamorphic or sedimentary is exposed to the surface, meaning wind and rain and other types of weather can meet the surface of that rock, it can be weathered and eroded to form sediment, which could then form sedimentary rock. And this happens when we have sediment that is deposited into lower lying areas like lakes. Technically, we would call a lower lying area a basin, but if it is deposited there, sediments will become compacted together just from all the pressure of these layers of sediment building on top of each other, and eventually the sediments will form rock. Okay, so this sedimentary rock typically happens on the bottom of lakes or oceans, and what I want you to realize is that there is a difference between weathering and erosion. Weathering is just the breakdown of rock, where erosion is the breakdown and transport. So you will see this week in the erosion lesson that the erosion is the already broken down rock that is transported. Okay, I want to quickly bring up this weathering lesson you completed last week. So we're not really going to specifically talk about each type of weathering. Yes, we have abrasion where rock is carried by wind and water. That's when it constantly hits the rock and shapes it. And a good example of that is Arches National Park. So that's from wind erosion. Wind erosion. So it can produce some pretty spectacular landscapes. So what I do want you to be aware of is that there are 2 types of weathering, mechanical and chemical. Mechanical weathering is where the shape of the rock changes only. Chemical weathering is where the shape of the rock changes, but there is also something new. A new substance is produced, and that only occurs with a chemical reaction. So that's why it's called chemical weathering. And this occurs from acids, either from living things like plant roots or decaying plants, or acid rain that is produced from pollution from factories. So I just want to point out, here's another example of chemical weathering, carbon dioxide, a compound, can combine with water in the atmosphere to form carbonic acid. So this is an example of how chemical weathering it produces a new substance. So carbonic acid is different from carbon dioxide and water. So carbon dioxide plus water gives you carbonic acid, a new substance that has different properties from carbon dioxide and water. So if you want to freeze this video just to check your work, please do so. Okay, so how are they alike? How are they different? And again, if you want to freeze this to check your work, that would be excellent. If you have any questions on the difference between chemical and mechanical weathering, please let me know. Mechanical would also go by physical weathering. So if you see that, it means the same thing. Okay. So we are back to my outline here. We talked about weathering and erosion. And one thing I do want you to be aware of, same thing with igneous rock, we can have sedimentary rock. And if that gets broken down and deposited again into a different area and cemented together, and those overlying layers are very heavy and they provide a lot of pressure, sedimentary rock can again form sedimentary rock. If sedimentary rock meets a subduction zone, so that's where two plates will meet each other. They're going to go towards each other. If one has a higher density, like the plate with the ocean over top of it, that is the one that will actually get pushed into the earth and has the potential to create metamorphic rock if it doesn't melt. So metamorphic rock is just heat and pressure. That's why it's these words are included here. If it doesn't melt, it can form metamorphic rock. If it does melt, it can then form igneous. So it looks like we can't have sedimentary rock that jumps right to igneous. It would have to go through the metamorphic stage first. So if we have metamorphic rock, it can also, if metamorphic rock forms at a specific location, from heat and pressure, if it gets pushed down a little bit further but still doesn't melt, it has the potential to form a different type of igneous rock. So we could have marble that could again be subjected to heat and pressure and form a different type of metamorphic rock. So each can form each other here. Okay, but we can't jump right from sedimentary to igneous. It would have to go through the metamorphic rock phase first. Okay, so if you need to look up diagrams on this on Google, that's fine. You can do that with your test. Your test is open notes. So if you want to use this video for your test, you feel free to. That's fine as long as you are using internet resources and not other people. The Exploring Uplift lesson from last week. Some of you did not really use the video to describe what was happening with the formation of the Rocky Mountains. So what you should have talked about, this is a normal subduction zone. So we have the denser oceanic plate meeting the less dense continental plate. So this one denser, if it has a higher density, it will sink below this plate with the lower density. So higher density, lower density, it's going to sink. What happened with the Rocky Mountains? This is not typical, but for some reason this plate that was being subducted didn't travel at a steep angle like it normally does. It came in at a shallower angle, and it kind of scraped. It's not showing it here in this picture per se, but it is showing the shallower angle, and it scraped the underside of the North American plate, and it caused those Rocky Mountains to pop up. So those Rocky Mountains were not right at the coast. So they're said about 1,000 miles from the coast of North America, from the west coast. Okay, so we're going to move on to plate motion and what happens at convergent plate boundaries. So we can have mountain building. So this occurs when we have two plates at equal density. So that would be continental to continental plate. So both plates with equal density. Okay. Or we could have a subduction zone. One plate, that's the oceanic plate, is denser. And that's what will cause it to sink below. And then eventually, this is where we could create metamorphic rock, heat and pressure, or if it goes a little bit below that, if it melts. So as you go closer to the center of the Earth, temperatures rise. If it melts, it could form igneous. And then through volcanoes, it could make its way back up to the surface. Another way magma can reach the surface is at divergent plate boundaries. If you have a divergent plate boundary in the middle of the ocean, you would have a mid-ocean ridge. One example of that is the Mid-Atlantic Ridge. So essentially, this is a underwater chain of volcanoes where magma comes out. Once it reaches the surface, it will be called lava, right? And then it pushes the plates apart. So I'm just going to, it pushes the plates apart here. So magma kind of fills this space, pushes the plates apart. Okay, so this is in the oceans. If you have a divergent plate boundary on a piece of land, so if you are in the middle of the continent like Africa, remember the East African Rift Zone? So you could create a rift valley. So same thing, we still have a divergent plate boundary. So plates are going in this direction, outward from each other. So this would occur on land, and same thing, what fills this spot right here is molten rock. So that's where we get a lot of volcanoes. So at convergent plate boundaries, we can have many volcanoes, we can have earthquakes. Since we have, we said that all plate boundaries are faults. We need a fault to have an earthquake. Okay, so we can also have volcanoes here and earthquakes. Transform plate boundary. So we have a convergent plate boundary, right? Transform plate boundaries where they slide past each other. We mainly just get earthquakes here. We don't have volcanism. We don't have any subduction zone. We don't have a mid-ocean ridge. One thing I want to point out about a mid-ocean ridge, this is where new crust is created. So we have igneous rock created here, and we call that seafloor spreading, because new seafloor is made at these places. Okay, so we have a transform plate boundary. We typically have earthquakes here. Okay, so I think we talked about a lot of the features that occur at these different plate boundaries. Well, let's see if we can get to the examples of essays. So let's take a look at example number 1. I want you to pause this as well, so you can take a look at some of the good examples here. I think we have time. I have a minute left of my recording because, again, I can't record past 15 minutes. So number 1, if the plates came to a halt in 1.5 billion years, then a couple million years after that, the Earth would look different. First of all, there would be no new formation of mountains because the plates would no longer be colliding together. Excellent. So we know, we should remember from class, I don't know if we talked about how the Himalayas are growing. So at this point in the future, no new mountains would be growing. In fact, everything would be starting to look flatter. A lot of you said that, which was good. So we still have erosion and weathering occurring because we still have the water cycle occurring. So we still have weather. So everything would look flatter. We would have less earthquakes. We would have less volcanoes. Volcanic eruptions would start to cease, if not stop completely. We would have no new seafloor being created, okay? And the continents would no longer be moving. So plate motion stops, plate motion scatter the continents, and the plates would no longer be moving, okay? Hopefully I covered what I needed to in this video. If you need more help, please send me an email. Thank you.